Hello, this video covers transition metal complexes. We're going to look at the formation of them and also how to name them. The colour of transition metal complexes will be covered in a later video. So transition metals have the ability to form complexes. Sometimes these are known as coordination compounds. The definition of a complex is it consists of a central metal ion surrounded by things called ligands. Now a ligand is an electron donor. So something that has electrons to spare that it can donate to the metal to form a complex. So ligands can either be negative ions. For example, the chloride ion can act as a ligand. The cyanide ion, which is Cn-, can also act as a ligand. Or it can be molecules with non-bonding pairs of electrons. For example, ammonia, there's a non-bonding pair of electrons on the nitrogen, or water. There's non-bonding pairs of electrons on the oxygen. For water, instead of writing H2O, when we're using it as a ligand, we write the formula for water as OH2. We put the atom that bonds to the metal first of all. So a ligand donates pairs of electrons to the central metal atom, or it could be an ion. And these form a type of bond called a dative covalent bond. Now a dative covalent bond is one where both of the electrons in the bond come from the same atom. So instead of a normal covalent bond where one atom donates one electron, another one shares another electron, both of the electrons for the bond come from the same atom. That's a dative covalent bond. You've actually already met something with a dative covalent bond, but you maybe didn't realize it, and it's the ammonium ion. Okay, ammonia is NH3. There is a non-bonding pair of electrons on the nitrogen, and when ammonia reacts with an acid or dissolves in water, it basically reacts with a hydrogen ion, but hydrogen ion has no electrons of its own, so the two electrons from the nitrogen are donated to form a dative covalent bond with the hydrogen. Now you can't tell which of these bonds, I know you can tell here because we've used an arrow, but in the actual ammonium ion you cannot tell which bond is the dative one. The four bonds are identical and the positive charge is delocalized, it's spread over the whole ion, which is why we put it in square brackets with the positive charge outside. So in this case the dative bond is shown by an arrow. There are different types of ligand, and they're classified as either monodentate, bidentate, and they can go all the way up to hexadentate. Mono meaning 1, bi 2, hexa 6. Excuse me. If a ligand bonds using only one donor atom, then they're called monodentate ligands. So for example, the chloride ion just bonds through the one atom, so it is monodentate. The cyanide ion, Cn-, bonds through the carbon atom, so it's monodentate. The ammonia molecule bonds through these non-bonding electrons on the nitrogen. Water molecules, even though there's two non-bonding pairs, just bond through this one oxygen atom, and the hydroxide ion bonds through this single oxygen atom, so they are monodentate ligands. Ligands that form bonds, that should be formed, through two atoms are called bidentate. Okay. So the most commonly asked about bidentate ligand is the oxalate ion. You can see that it's got two oxygen atoms here, both with a negative charge. So overall the oxalate ion has a 2 negative charge. It can form one bond to a central metal ion through this oxygen and a second bond to the same central metal ion through this oxygen. So it's bidentate. En, or ethylene diamine, bonds through these two sets of non-bonding electrons on two separate nitrogen atoms. Okay, so the non-bonding electrons form a dative covalent bond with the metal from this nitrogen and to the same metal or metal ion with this nitrogen as well, so they're bidentate. The only hexadentate ligand that you're likely to meet in advanced hard chemistry is the ethylene diamine tetraacetate ion, which nobody calls it that. Everybody just shortens it to EDTA. Okay, now it's hexadentate, which means that it's got 6 atoms that it bonds to the central metal ion through. Okay, in fact, it's 6 non-bonding pairs of electrons. You can see here we have 2 oxygen atoms, so it can bond through those 2 oxygen atoms. It can also bond through the non-bonding pairs on these 2 nitrogen atoms, so that's 4, and then another 2 down here, these oxygen atoms, giving you 6 different atoms that it can bond through. And in fact, this is a diagram that represents what a nickel EDTA complex is. There's the nickel, the metal ion at the center, and here are the 4 oxygen atoms from the EDTA molecule, EDTA ion, sorry, and the dative covalent bonds to the nitrogen as well. So this is 1 molecule of EDTA bonding with 1 ion of nickel. You should know all of these ligands, okay? You should know whether they're monodentate, bidentate, or hexadentate. There sometimes are problem-solving ones where you're asked to work it out, but these are the most common ones, and you should know what type of ligand each of those is. The total number of bonds from the ligand to the central transition metal is known as the coordination number. Now, the coordination number is one of the easiest things in advanced higher chemistry. If you can count, you can do coordination number. So here's the metal in the center. You can see that there are 2 bonds to it, so the coordination number is 2. In this example, metal in the center, 4 bonds, coordination number is 4. Here, again, it's a tetrahedral arrangement this time, metal in the center, 4 bonds, coordination number 4. And this final one, coordination number 6, because we have 6 bonds to the center. Now, what's important to know is that the coordination number is not the same as the number of ligands bond. In these 4 examples here, we've got 6 ligands, and the coordination number happens to be 6. Here, we had 4 ligands, coordination number happens to be 4, and so on. If we go back to our nickel EDTA complex, we have 1 ligand, okay? That EDTA molecule, there's just 1 of them. But the coordination number is 6 because there are 6 bonds to the nickel ion in the center. Okay, so coordination number and the number of ligands bonded to the central metal ion are not always the same. You should be able to do questions 51 to 56 on transition metal complexes now. Okay, if we have a look at naming transition metal complexes. Now, this changed, well, not necessarily the SQA changed it, but the way that they are going to examine you on this changed last year. So if you attempt any past papers, with the exception of the specimen past paper, then the rules will be slightly different. You may get the answers may be different to what you would expect. Okay? So just be aware of that if you're doing some older past paper questions. All of the questions I will set you and the check tests have been updated to reflect the IUPAC rules, which is the International Chemistry Society. So first of all, when we are writing names and formulae, if we're doing the formula of the transition metal complex, we write the symbol of the metal first of all. Okay, and then we write the symbols of the ligands. Now the symbols of the ligands are put in alphabetical order according to which atom of the ligand binds. Okay, now I mentioned this earlier, that when you've got water as a ligand, we write it as OH2 because the ligand, the non-bonding pairs of electrons that form the dative covalent bond with the central metal ion are on the oxygen. So we write the oxygen first of all. If, for example, we had a chloride ion ligand and we had a water ligand in a transition metal complex, you would put the chloride ion first of all because Cl comes before O in the alphabet. So in the formula, it has to be in alphabetical order according to which atom of the ligand that binds. Okay, with ammonia, for example, ammonia would come after chlorine but before water in the formula. Okay, And if we just highlight the fact that it's oxygen that binds to the metal and water, so that's why we write it as OH2, only in this instance. We put the formula of the complex ion in square brackets. And then the charge for the complex ion is outside the square brackets. So this one here, you can see that we've got 2 chloride ions and 4 water molecules. So the chloride comes first because alphabetically C comes before O. The overall charge on this complex ion is a single positive charge. When it comes to naming the ligands, slightly different rules. So when you put the name in, now we're looking at alphabetical, but we're looking at alphabetical in terms of the name. Okay, so the name of the ligands are in alphabetical order based on the actual name rather than the atom that it bonds through. And then the name of the metal comes out last, followed by its oxidation state using Roman numerals. If there's more than one of each type of a ligand, then you have to use your prefixes, okay, like di, tetra, penta, hexa. Wouldn't go any higher than hexa. If your ligand is a negative ion ending in "ide," then the complex name, in the actual complex name, then your ligand, you put an O on the end. Okay, instead of IDE, it becomes IDO. That's one of the changes. So for example, chloride becomes chlorido, cyanide becomes cyanido. If you have hydroxide, it becomes hydroxido. Bromide, bromido. Fluoride, fluorido. Okay. If it's ammonia, that's your ligand, then it's named amine. Watch the double M there. Okay, it's important that has a double M. And water is called aqua. If overall the complex, so the bit in the square brackets, has a negative charge, then the name of the complex will end in ATE. For example, if you have a complex containing a complex with a negative ion that contains cobalt, then the ending of the name will be cobaltate. The exceptions are for copper, okay, and for iron. So for copper, we don't say copperate, we say cuprate. It's from the Latin name. And for iron, we don't say ironate, we say ferrate, again from the Latin name ferrum. If the complex is a salt, so it has both positive and negative ions, just as normal, then the name of the positive ion precedes the name of the negative ion. Now this probably looks highly complex, no joke intended there, but these rules are hard and fast, okay, so they don't change. If you follow these rules, you can always write the chemical formulae for a complex and you can name a complex. When this came out last year, the SQA were quite clear that they're not going to expect you to be able to write exceptionally complex names or formula that will be asked in a straightforward way. My understanding is that it's probably a multiple choice where they will give you options and you have to work it out. Okay, but that, again, that's my understanding. That's not a hard and fast rule. So you can use the information above to write the names of the ligands. So ammonia, remember we said was amine with the double M. All of these ones that end in "ide," you remove the E and replace it with an O. So bromido, chlorido. Oxalate becomes oxalato. And water became aqua. So notice that water, remember, was OH2. The oxalate's another one that changes, okay? It bonds through the oxygen atoms. So that's O4C2, and with overall a 2 negative charge. These are the most common ligands, and these are the ones that you need to know. You need to know whether they are neutral and whether they have a charge on them. So we're going to have a look at some examples and work out how to name them. Okay, so if you're given the formula, how do you name them? First of all, look at how many ligands you've got, okay, and decide your order in the name if you've got more than one ligand. So here we have 4 water molecules, okay, so tetra aqua means 4 water. We don't have any other ligands, so the next bit is copper. We know it's just copper because the overall complex doesn't have a negative charge, so we don't need to change it to cuprate. These water molecules have a neutral charge. Overall, the complex ion has a 2+ charge. Okay, so the oxidation state of the copper must be 2. Okay, metals will always have positive oxidation states. If you've got a negative oxidation state, something's gone wrong. So tetra aqua copper 2 will be the name of this complex. For the next one, we have 6 ammonia molecules, so that's hexa and then amine to represent ammonia. Ammonia molecules have no overall charge, so have an oxidation state of 0. So therefore, this 2 positive charge on the complex ion must have come from the oxidation state of cobalt, which is +2. So hexa, amine, cobalt 2. For this one here, we have 6 cyanido ligands. Okay, now the cyanide ion has a single negative charge. So the oxidation state of all of these cyanide ions, okay, or cyanido ligands, is -6. The complex ion overall has an oxidation state of 4-. So therefore, in order for -6 to become 4-, the ion must have an oxidation state of +2. So we have hexacyanido to show the 6 cyanides ions, and then ferrate, because this is iron, and overall we had a negative charge on the complex ion, and then 2, which is the oxidation state of the ion. The next 2 examples are salts rather than ions. So just as we would, this is going to have any old salts. Even if there's potassium chloride, you'd always have to put the potassium first. So the positive ion, potassium, goes first. So with potassium, and now we're just naming the complex ion as we had done before. Okay, so we've got 6 cyanido ions. Again, we know that the charge on just this complex ion bit, just this bit here, will be 3-. And you might be thinking, well, how do we know that? We know that because there are 3 potassiums here. Okay, potassium has a valency of 1, and there's only one of these complexes, ions, so therefore the charge on this would have been 3- to make overall a neutral salt. So because this chart has a 3-, we will have ferrate at the end. Again, the cyanido ion has a charge of -1, so overall it's -6 for the oxidation state of the 6 cyanido ligands. The complex has a charge of -3, so therefore the oxidation state of the ion must have been +3. So this is called potassium hexacyanido ferrate 3. This time, this part is a positive ion because we've got chloride at the end. So chloride is our negative ion. Okay, it's not part of the complex. Chlorine here does not exist as a ligand because it's not inside the square brackets. We have 6 waters, so hexa aqua. We can work out, because we know chloride ion has a single negative charge, so this has a charge of 2-, so therefore our complex must have a charge of 2+. Because the water molecules are neutral, the 2+ comes from the oxidation state of the cobalt, so it's hexa aqua, can't say that one, hexa aqua cobalt 2 chloride. Okay, have a go at naming these complexes. I understand it'll look quite daunting to start with, but follow the steps and see how you get on. And these are far more difficult than any you will get to actually name in an exam, particularly the last 2. The last 2 are salts, okay? But A to G, you're just naming the ion part of it. Okay, at the next step, we're going to have a look at writing formula for the following complexes. So if it's got diaqua, dicyanido, so you know you've got 2 waters, you've got 2 cyanide ions. You need to work out which one's going to come first in the formula. Okay, so obviously we'll have the metal first, but which of the ligands is going to come first? We've got the single copper, Okay, and it's usually in a complex ion, it will just be a single metal. And then looking at your atoms that it bonds through, the cyanide ion bonds through the carbon, and the aqua, the water one, bonds through the oxygen. So C comes before O, so you're going to have your 2 cyanido ligands followed by your 2 water ligands. Then you need to work out the overall oxidation state. I think I'm going to type this one just to make it a bit easier to see. So far we've got our 2 cyanido ones, our 2 water ligands, and we have to work out whether this complex has an overall charge. Okay, we know that the water molecules have no charge. Okay, so they're not going to contribute to any overall charge. The copper has a +2 oxidation state because that's given in the name. The 2 cyanide ions have a -2 oxidation state, so we've got a +2 and a -2, so overall this complex has no charge. So those are the steps that you would go through in order to write the formula. Okay, like I said, these are much more complicated than the ones you can be asked in the exam and by the SQA. The F and G are salts. Okay, have a go at them. Any questions, please just ask. You can also do questions 57 to 60 in addition to the check test for this section. Thank you.